welcome. So, we're going to go through geology in the Spratly Islands region, and particularly this oceanic plateau region, which isn't really an oceanic plateau, but let's go. So, and as well as Falkland Islands, so we're going to start there, and then we're going to head over here to the Falkland Plateau. So, in recent episodes, we've been talking about oceanic plateaus like this one, Ontong Java, Manihiki, Hikarangi, and their formation with regard to the Earth's expansion process, where undercurrents below the crust, which can be mapped by this map, flowed out in all directions from Pakistan, from this swirl location, flowed out in all directions, and all the continents were conjoined. So like it flowed over here and then didn't flow here initially because it flowed directly into North America. And then it collided with currents flowing in the other direction in this region where Australia was adjacent and Western Pacific was over here. So real quick, like this. The Western Pacific was really all the way on the eastern coast of the United States initially. When this was the process was beginning, Australia was over here atop this, all these circular regions, which are visible, like circle. There's a bunch of little circles in here. Visible there, as well as visible here, like a circle there. Circle here. But anyway, so Australia was atop that, and the Philippines were here in this region of the Exmouth Plateau, and then Borneo was down here, like this. As well as Sulawesi and North Maluku are here, and this region of Papua New Guinea was like folded inward. Before the Earth expanded, these segments of the crust were conjoined to Australia, which were then conjoined on the opposite side to North America, like this. Okay, so with that in mind, let me close all windows there. We're going to look at Spratly Islands, which is adjacent to Borneo. So recently I made this. I don't know how I feel about it exactly in terms of if it's precise enough, but I was talking about how Spratly Islands seem to be generally between this and this structure. Certainly these don't align with the southern portion very well, which I still haven't really thought about exactly. My guess is they were more folded upward to be in line with this initially, but as the Earth expanded, it like realigns more like down here, and possibly some other added accretion type things going on. So this region is really what we're looking at. This isn't necessarily in regard to this image, more so just geologically trying to get a bearing on the information. In terms of this map, here's Borneo. Spratly Islands are here. And the Western Pacific had a current flow that got segmented by another current flowing inward over this way into here, which segmented the current. Like a current was flowing, another current came in and dissected it, that then made it divide to go like this southern direction and this northern direction, where it then ran into resistance up here and bent down this way and basically propagated along the western margin or eastern margin of Eurasia and pushed out islands, arcs in the process, later in the process, but essentially flowed down this way to induce the arc of the Indonesian archipelago here that has like an arc at the end, as well as an arc up here, like a wave. So like a propagation of energy this way that created a wave structure this way. So essentially a current was flowing down this way. And there's the Spratly Islands. So with those concepts in mind, I just checked out the Spratly Islands, and this is what I found. Did a quick search on Google Scholar to try to find. I'm not sure. The part of the issue is I'm not sure what the terrain is called. Not the islands themselves, but the crust around it. But most of the information I found was from Wikipedia, which is fine as a starting point, so we're going to start there. Wikipedia describes the geology somewhere. Okay, so it has, of this region as a whole has horse, which are these things, and grabens, half grabens. So like Horst and a graben has horse on both sides. Half graben has a horse on one side. I guess that's the difference. I'm certainly not completely aware. Maybe it's more to do with the rotation than that there's this tilt that's leading to half grabens, I guess. But this region is composed of horse, half grabens, rotated fault blocks, so probably why it's half grabens, parallel to magnetic anomalies of the adjacent oceanic crust in South China Sea. So over here, adjacent to this, is parallel magnetic anomalies that really are running this way. Or maybe they're running this way. Not completely sure. If they're running this way, then they're probably from this current going over here and going generally across this way. This block was moved from over here. But going generally across, deflecting off of pressures of Australia as it moves Australia into a final position, like it runs into more resistance, which then deflects that way. So possibly with some relationship to those, I'm not sure which they're parallel to, but there is a parallel relationship between the Spratly Islands, horse grabens, and the adjacent magnetic anomalies. Just based on this, I would infer that they're talking about in this direction and not this direction. But it didn't specifically say the direction, just that they're parallel. So that gave me the impression that there's this current flow going generally here that also is going here, that's going underneath a crust that is then like thinning the crust and leading to cave-ins that lead to horse graben structures, basically, where the current flow went through channels like underneath the crust. It didn't go in just like a continuous layer beneath the crust. It went in more of like in fingers and channels where it could get into underneath the crust. So this crust consists of stretched and subsided continental crust. So not oceanic crust, it's considered continental here. Although this is what's interesting about that. Associated, or of Cretaceous through or Triassic through Cretaceous strata, which is 252 after the Permian Triassic, which interesting because 252 is what I would interpret to be like the first expansion step. So the Earth expansion process had build up from 541 largely to 252, and then at 252 there was a step of expansion, which was when this seems to have formed. I don't know if it has any early Precambrian crust at all in the Spratly Islands, and if that's the case, then it's not really the same as other continental crust. It's kind of like a temporarily forming continental crust that was unstable because of its location, but was able to form initially because of just the pressures. And like the crust was breaking, but not enough to sever apart at that time. So in the interim, it formed like a continental crust of the Spratly Islands region that is of Triassic through Cretaceous, but then at the Cretaceous 65 million, which is interesting that it was in that time frame when this crust formed. At 65 million is when the continents like physically broke apart so that they could then physically move apart from one another by undercurrents filling in the space and forming oceanic crust. Not all oceanic crust is formed then, but that's when the Earth really expanded. Up until then, it was building up pressures and forming like portions of the Atlantic, but not really breaking the continents apart so much so that they could freely expand, kind of like breaking bonds in a molecule requires an activation energy, and the activation energy was being input, but it didn't actually reach the amount of activation energy until the Cretaceous, when then things could freely break apart, which at the end of the Cretaceous, which is why the mean age of the oceanic crust is 66 million. Age of the oceanic crust does not go back further than 200. This is not answering it. We need Muller et al. Or 64.2, so slightly less than the boundary of the Cretaceous Paleogene, the KPG-KT boundary. Okay, so this is forming in that time frame, which gives me the impression it's kind of wedging in and pushing the continents apart, but in a way where it's forming temporarily just continental crust, but it's still unstable because of its location. Like that's where the currents are also kind of colliding, interacting the most, which is why the Pacific is the Pacific, like because this is where the most interactions of the undercurrents were colliding and leading to severing of the continental crust more so. But in the interim, it formed this, it seems, based on Wikipedia. Let's find the specific thing. Maybe Triassic. Maybe we can find probably that one. PDF. Nope. Let's try ResearchGate. Request full text. Two recently acquired regional multi-channel seismic profiles across the southern margin, the South China Sea, are interpreted. One line is crossing the entire Nansha region from the deep oceanic southwest subbasin of the South China Sea. So from over the southwest, so I guess over here, the subbasin, I guess over here. Along the Nansha Islands, too close to Borneo. Borneo being this. Nansha Islands, I'm not sure which ones that is. It's just saying Spratly Island, so maybe that's a synonym, another name for them, depending on who named them. The other one runs east of the Reed Bank. Based on the interpretation of these profiles, worked out stratigraphic sequences. So this is basically where it comes from. 5 tectonic stratigraphic units are determined, together with 7 sequence boundaries. Detailed analyses on the extension factors based on the measurement of fault heaves reveal 2 episodes of continent extension. So kind of like building additional material on the continents, that is continental crust, separated by a distinct unconformity, which likely correspond with the beginning of seafloor spreading in the South China Sea. So when the Earth started to expand rapidly, so that then seafloor started to form spreading, which then led to basically, like, imagine there's something contained between 2 walls and one of the walls moves away, it kind of can extend. Continental extension separated by early extension occurred during continental rifting, late Cretaceous, so like when the Earth started to rapidly expand, through the early Oligocene, which is Oligocene, is around 34 million years early Oligocene, and resulted in formation of half grabens and rotated blocks controlled by a deeply rooted detachment system. Extension continued in our study area during the drifting phase of the eastern subbasin of the South China Sea. So 20-something million. Oligocene, again, is 23 million late Oligocene through the early Miocene, which I guess is around that time frame. So somewhere around 25 to 22, let's say. Just approximating by those, until a subsequent opening of the southwestern subbasin at about 25 million. But then its intensity, the intensity of extension, decreased markedly thereafter. So after around 25 million, essentially, like what I would say is the oceanic floor started to build up pressure enough that this extension had a new wall come in that held it together enough. So it's a markedly decreasing in intensity thereafter. Deeply rooted detachment systems evolved possibly during this second phase of extension at continent-ocean transition area. Okay, I don't know if we can read more. Okay. We suggest that a widespread carbonate platform developed across the dangerous grounds. I'm not even sure where that is. So, dangerous grounds. Geology. Spratly Islands. I don't know. The northeast part of the Spratly Islands is known as dangerous grounds and is characterized by many low islands, sunken reefs, and degraded sunken atolls. So northeastern part, kind of like where there's current flow. So imagine a current flow is coming this way along the eastern margin of Asia to Indonesia, and then under this continental segment that had formed of the Spratly Islands, then its first encounter is going to be in the northeastern portion of the region. So it would make sense that the northeastern portion would have the most sunkenness. I'm not sure exactly where it's referring to still. Like, this looks maybe like it came in through here, really. But to a point where it's called the dangerous grounds. Concurrent with the drifting period of the southwest subbasin of the South China Sea, fault-related stretching factors J to the west and east of Reed Bank are found to be comparable and show discrepancy with the whole crust stretching factors. Fault-related stretching factors to the west and east of Reed Bank. Let's see, Reed Bank, Spratly. Almost. Reed Bank, Reed Table Mount. Okay, so is a Goyet. Presumably this, then this. So it looks like it even has like a shape like a current one around it. Almost like a pillar that the whole thing had like weight on to compress this region more to a point where it basically went around it like a nucleus. Let's see if that makes any sense in this context. Fault-related stretching factors to the west and east are found to be comparable, which kind of makes sense if it's going around a mass, that it would be comparable in terms of going around it. On each side, comparable stretching factors. Show discrepancy with the whole crust stretching factors in the study areas derived from gravity modeling. Thus, we conclude that the continental crust of the southern margin might have experienced depth and dependent extension, like undercurrents were present, that I guess were at different depths. Okay, so earliest period of tectonic stretching of crust associated with the late Cretaceous. So back to here. Earliest period of tectonic stretching of continental crust and formation of horse grabens and rotated fault blocks, association with the rifting and later seafloor spreading during the late Cretaceous and early Oligocene. So associated with the late Cretaceous and early Oligocene is when the stretching occurred, because that's when the rapid phase of the Earth's expansion process was happening. Beginning really was around 66 million, which is what actually is the KT boundary, is the rapid phase of the Earth's expansion process, and not to do with a comet or asteroid or whatever hitting at Chicxulub, which is actually the result of current flows, which I'll quickly just draw to currents of Earth. So just following this line from over here, we follow this very straight path through Canada that then separates this way and this way. Separates, goes around, and then also goes over here and over this way, but begins to vibrate sort of going this way through this region, through Flathead Reservation, associating with the Missoula flood because radiometric dating is not really that good of a method of like putting things in a sequence, particularly when different methods are used, like uranium, lead, and carbon are not good to use together, like, and put on the same time scale. But this flowed over this way, wobbled through here, continued over this way, where then it ran into resistance out here and bent around and went this way, and then through here and basically spiraled in. Energy got trapped in this region by high pressure because there's water over here flowing in eddies atop the Hudson Bay as well as Michigan, and just generally over here during the flood, filling all of this with high pressure of the water itself, so that when current flowed this way and tried to go back because it was running into other resistances this way, some of it went out this way, some of it went out this way, but some of it bent back as well as went forward through, but some of it bent back in here and just kind of swirled and swirled until the pressure built up so much that Chicxulub occurred, which is really what caused Chicxulub. And then those currents continued. There's also current coming off of Hudson Bay, opening the gap over here, swirling against Africa in this region, beginning initially closer, but just like opening a space, getting bigger, with Bermuda as like a focal point, although maybe I didn't draw it that well. And then all currents coming off of Africa, interacting, creating the Azores Plateau. The current from Hudson Bay went atop Azores Plateau, went to the west of it, and then current from Africa went below it, which then created three sides of like a triangular, like bent triangle of the Azores Plateau, where some of the current that went from Hudson Bay north of Azores Plateau went into the Mediterranean and across Europe, while current from Asia swept across Africa, interacted with that current from Hudson Bay across Mediterranean, but made it across Africa all the way over here where there's pressures over here. There's lots of pressure on the western margin of the Americas that held this water on the Americas, and so when this water from Africa came across, it interacted with water from North America that then created like a boundary, held a boundary over here, and bent back, and then came across this way and held that boundary, held this boundary, and just basically interacted like so. And here's Falkland Islands we're about to get to down here. And then here's the currents from Asia coming across the Baikal Lake and going center point of the Himalayas to Damodar Kund and Kaligandaki Valley, etching a path through there, but then going off the edge this way, as well as going more so this way into the Mediterranean. And then here's some more of the currents in North America. Okay, so that's going on. And what was I talking about, though? Essentially, those currents are involved in the Earth's expansion process, and I'm trying to remember why I was talking about that. Oh yeah, the KT boundary. That essentially when the Chicxulub happened was really the breaking of bonds between continents, which then led to probably, honestly, my guess is it detached the Western Pacific plate, this region. It detached it from over here, and it was able to freely slide out like this. Like it literally was here at 65 million, forming below. Here's North America, forming below North America as this plate. So like its entire structure was forming, incubated under North America, but then it slid out from under North America. Let's look here, like where this bend is. Chicxulub's here. Generally at this bend where this current goes across, like right there, maybe, was it there? Generally there. So almost certainly it was like putting a pressure down to a point where the plate below the crust, which had pressure pushing it sideways, but it was sitting there in the way. Like it couldn't move as easily because it was solidifying. The pressure down was able to detach it, and it then slid out this way and became the Western Pacific, but it was already preformed. Like it had North America above it. The mid-Pacific mountains were forming along this region. So it really detached the plate and allowed the Earth's expansion process to happen, but it was all a culmination of all these things going on, where current was being focused that way above the crust as well as below the crust in forming the plate of magmatic currents that then were like basaltic in nature, which led to the ocean floor. But then it broke away and the Eastern Pacific formed. So if we look at like oceanic crustal age, the Western Pacific is significantly older. So like here, anything around the orange in this region is new, but the Western Pacific is older. So it's forming the Western Pacific in the time frame of like 100 to 180 million in this time frame beneath North America, radiometric dating wise. Not in actual time, because this was much more recent during the Earth's expansion process when the global flood was happening, which is what those currents were mapping. And at 65 million, it was able to break it away, break the bond between this underplating of the Western Pacific and the base of North America so that it could slide away, and then the space between got filled with the flows of undercurrent. So like as it moved, this current here, which was flowing all the way from over here, it flowed this way, up here, over this way, and then across into this region, and then down over here. It was then able to flow out into this region and fill it, and began to form new oceanic crust. And it met a counterbalance of currents coming from this way, probably also from down here. Current flowed also not just westward, but also southwestward down through Africa, through the East African Rift area, and then continued through, I believe, western Antarctica, through this region. Whatever this is, it might be eastern, I think it's western, and then flowed through Australia, but it also ended up going over this way and up into here. So that's interacting with current from over here as it's filling in the space. which is also interact. Let's say, just hypothetically, it's forming this region, which is then maybe interacting with current flowing in from here that went across into this region, and then some current went into this region and kind of formed that segment, where other current went across from Africa into southern South America and filled in this region, something of that nature, underneath the crust, including the oceanic crust, to like pressurize this entire eastern Pacific and then form the crust, not under continents, where the western Pacific did form under continents. Okay. So, starting late Cretaceous, let me just make sure I read the previous line. Second period from, okay, let me start back a couple. This one I already read. Earliest period of tectonic stretching of crust associated with late Cretaceous and early Oligocene, which then had a period of hiatus because a second period from the late Oligocene, so in the middle Oligocene, there seems to have been a hiatus in terms of the stretching of the crust. Second period, late Oligocene through early Miocene, additional stretching and block faulting. And then it said, starting in the late Cretaceous, when the Earth was rapidly expanding, fine-grained, organic-rich marine sediments accumulated in the half-gravens within the dangerous zone region. So now that we know where the dangerous zone region is, which is, I believe, up here, it's generally in the northeastern region, accumulation from current flows in that direction. Like, they're not accumulating over here. They're accumulating at the boundary of the current flow in this region, where the current flow, similar to down here, happened over here too, where there's extension basins down here that got filled. 2 episodes ago or so, I talked about this region, whichever, maybe 3, in depth about the nuances and analyzing its relationship to this, and really shedding light on that there is a current flow that went this way, but really in North America it went this way. It went northward in North America. From the perspective of North America, it went northward. From the perspective of Australia, it went southward, because Australia's southern direction, like this is the north of Australia, Papua New Guinea, and then northwest, and then western, and then southern, southwestern. So it was going south from the angle of Australia here, which then led to the filling in first, and I forget one of the layers. It filled in this region first, and then it swept across the whole thing, according to dating of the layers, which fits with a current flow. So we're seeing a similar thing here, essentially, where starting in the late Cretaceous, fine-grained organic rich sediments accumulated in half-gravens within the dangerous ground zone. And then localized regions favorable for accumulation of sediments that might contain oil gas reserves is something else they mentioned. I just kind of wrote that down. So my interpretation, in short, is that this was a continental crust that perhaps was like temporarily forming, but it wasn't stable because it didn't have this like support structure. Its support structure was undercurrents of magma based undercurrents of basalt, like this material, but flowing. So it supported it for a time, even magmatically, and then it stopped flowing, but there wasn't really a support structure anymore, and so it caved in by pressures, particularly etching through it, of current flows going this way that then etched into it. So that's Spratly Islands. Let's open up my downloads. Falkland Islands. This one. So this is with Dave McCarthy. I'll link this YouTube video. I'll watch this YouTube video. So that's what these notes on Falkland Islands are. Geological controversies of Falkland Islands, wave, tsunami, impact, and spinning plates. I might have taken a picture. I must not have. Before this slide, I'm pretty sure he said the controversies are waves, i.e. tsunamis, impact, whether or not there's an impact, and spinning plates, whether or not there's spinning motion that occurred. Don't know if I'm going to be able to find where in the notes. So these are just the layers. So the West Falkland group, Falkland parts of Gondwana. There's Proterozoic, so it's definitely, this is unlike Spratly Islands. There's evidence of before the Earth's expansion process, which is pre-Cambrian. The Earth's expansion was Cambrian through Holocene, so like here onward. So all this stuff is during the Earth's expansion process, but because there are Proterozoic materials, it really points to that this region pre-existed the Earth's expansion process and the global flood. And this region, like depositions afterward were formed in the flood. These mudstone, sandstone, mudstone, sandstone, mudstone, sandstone. During the flood, before the flood, granite, gneiss. Although one of these, I'm not sure what that is, diamictite. Let's just look it up real quick. Diamictite. Sedimentary rocks is sedimentation. Sedimentary rocks forming during the flood, which kind of fits with them forming during the flood. Okay, so let's keep going past that slide. Gula Falkland fracture zone extends to eastern South Africa, I guess I wrote. Let me just start here. So that, as we can see, there's nice amphibolite hornblende from 1 billion radiometric dating. These are all before the flood, before the Earth's expansion process. 1 billion, 1 billion, 1.1 billion, all pre-flood, really indicating that Falkland region was continental crust. It was pre-existing crust before the Earth expanded. It didn't form in the Earth's expansion process. It was certainly influenced by it, but it didn't, like the Spratly Islands, it didn't, or unlike the Spratly Islands region, it did not form during the Earth's expansion process. I might be wrong about Spratly Islands. It's my suspicion, based on what I've seen at least, that they formed during the Earth's expansion process, just because Triassic through Cretaceous equals Earth's expansion process. Triassic 252 through Cretaceous in this period. Even if it's called continental crust, it's still formed in the Earth's expansion process. Okay, so let's keep going past that. We're maybe a little less interested in the pre-expansion portions of the Earth right now. I mean, it's certainly worth noting. Very, very gray, very Mercury-like. West Falkland Group, 7.6 kilometers thick succession of largely gray, unremarkable rocks. West Falkland Group is from the flood period starting in the Silurian through the Devonian, so like 430, let's say, through whatever that is. I forget what that boundary is. Like 350s. I think if we go back, 358. Largely deposited in a shallow marine environment. Abundant fossils, mind you, fossils like we talked about in the last shallogram episode, can be mislabeled. So whether or not they're actually fossils or just look like them is unclear without closer inspection, but from that angle, I know at this point we kind of accept things that have been labeled as fossils or look, the more complex they look, the more we just label them fossils without thought. And surely this could never happen by the Earth geologically. But like, there's evidence of things that we've called fossils that have been determined to not be biological. So it just points to, in coupling with shallograms, which really demonstrate that ammonites are not fossils, the potential of the Earth to do things like this. So I'm not completely sold that they're fossils, but besides the point, it may be that they're fossils, but it's uncertain. Okay, let me keep going. Maybe I can find. Here's a picture of the Phonia group from Permian and Carboniferous. Medium and fine-grained sandstones, siltstones, mudstones, rare tuffs, so volcanic ash, and tillites. Detritus from a volcanic includes detritus from a volcanic arc which lay on the margin of Gondwana. Okay. Structural geology of Falkland Islands. It's been a couple days since I looked at this. Hopefully, this was pretty complex. I was just taking pictures of pretty much every slide, honestly. The Phonia, which we were just looking at there, from this period. Also, oops. Yeah, the Phonia. This one, I guess, is over here. And then, whatever this is. Gondwana Fold Belt Deformation 255, which I found really interesting. It's very near what? The Permian Triassic boundary, which again points to a stage in the Earth's expansion process that was highly relevant at the Permian Triassic boundary where the crust was breaking apart. Where it did so down here, it deformed in this region, but it didn't create a large igneous province by like rupturing and venting pressures as it did in Siberia. Southward verging fold and thrust belt. Although across the rest of Gondwana it's northward verging, which I believe relates to whether or not this rotated. Like one of the details that points to that it rotated is that the rest of the Gondwana had a different direction of the fold and thrust belts that are considered associated. And then there were dike intrusions, So intrusions through the crust, which we see here, I believe in, these are anomaly indicating normal magnetization, reverse magnetization. Not sure if those are the pointing to the dike swarms or intrusions. There's definitely a dike swarm circled there. Dike over Pebble Island dike. I'm not completely sure, but there's two phases of dike swarms, one in the Jurassic, one in the Cretaceous, which points to pressure buildup in that time frame. That's like seeping through as dikes and venting the pressures. Bathymetry, so the Falklands Plateau and then the oceanic crust, like it's, let's see, around, let's say 3,500 meters below sea level, where the oceanic crust is more in the 5,500, so it's like 2 kilometers above the oceanic crust to the Falkland Plateau. Although he pointed out there's not much data. Which reminds me, I meant to look at this area on this map. It's probably not much to glean from it because it just is going to look like the other maps, but we want color shaded relief. So there's Falkland Islands, but then the plateau extending out here. Falkland Escarpment. North Scotia Ridge bounding it. With that, which I'm pretty sure I called it by something else in this presentation. So let's just keep going. That wasn't much to see from that. And then he talked about using the gravity anomalies of the region and really seeing details that aren't present otherwise. Let me see if I can catch up. Let me just read because I definitely passed what I saw here. So going back to around here, let's say 1 billion year metamorphic overlaid by 400 million year old rocks, i.e. a 600 million year unconformity. So there's an unconformity, he pointed out, in the Falkland Islands, which is definitely worth noting. 600 million years of nothing depositing is only explainable, in truth, by the fact that that amount of time did not pass and the flood happened, and that deposited the 400 million plus year old deposition of sedimentary rocks. And before then was just pre-existing a stable Earth when nothing was really depositing, relatively speaking, until 400 million when the flood happened again and deposited these overlaying rocks. Cape Meredith Complex 1 billion, West Falkland Group 440 to 358 million, Livonia Group 320 to 252 million. Just before deformation in the Livonia Group was being deposited. Deformation from 255 to 250 widespread across southern Africa and South America, which continued until the mid-Jurassic around 160 million. I'm just thinking how that might relate to the formation of the Western Pacific under North America, if there could possibly be some relationship. So, dike intrusion phases from at approximately 180, second phase lower mid-Cretaceous 135 approximately. Onshore geology then ends. Everything onshore at Falkland Island. At least when he said that, maybe something else comes up that is later, but ends at the dike intrusions at what he said to be 180 and 135. I believe, I'm not sure about 180. I just kind of guessed and wrote that, and I wrote 130. Later he said 135 for this second dike intrusion, so I adjusted it. I know that one's at 135. The Phonia group made up a fine-grained material with class. So let's keep going to the Laphonia group. There's class in this. Here's granite clast. Granite clast. Part of islands being pushed to south while rest of Gondwana pushed to north. I guess that was with regard to this. And then east-west Jurassic, east-west, east to west Jurassic dike intrusions, and northwest. So north. I'm not sure about. I guess north, like the. He said northwest. I guess he meant northwest, southeast. Jurassic dike intrusions. So east-west, and then northwest, southeast, and then north-south. Early Cretaceous dike intrusions. So I guess these blue ones are more early Cretaceous, where the red ones are more, at least this region. Maybe not by color. The color is definitely by author. Unclear, but essentially there are east-west Jurassic dike intrusions, whereas early Cretaceous is north-south. I didn't have much to make of that at the time. Here's the dates, actually. The exact dates. So it was around 180. I guess there were 2 dike swarms, and then there was a phase of dike swarms around 135. Yeah, northwest. Like I think he meant northwest dash southeast. Or maybe he meant north to west, so southwest northeast kind of angled. I don't know. I've never seen that way of saying it. Okay, there's that plateau. Okay, now we're kind of catching up. Gravity. It said Eye of Faith. Something's called the Eye of Faith. I think it was here. Or here. One of these is called the Eye of Faith. I just kind of wrote it down. Okay. Then they did some seismic. I didn't fully capture this image because I only took this one after this second image was put up, where basically they have a source that puts energy into the ground that then reflects off of the layers, and then they capture the sonar or whatever they're using over here, which then determines this image. So we can kind of see like a boundary, some kind of fault line type thing, whatever it might be called. And reflectors and faults. So I guess reflectors being different layers and faults being like breaks in the layers like this. Falkland Plateau, oceanic crust. They're finding also it's like Precambrian basement rock. Precambrian before the Earth's expansion process began. And then this is during the Earth expansion process. Okay, Falkland Plateau Basin. I wrote east of islands towards far plateau. So like over here and here's the islands to the east, I guess right there, where is where this measurement right here is. Significant thickness of Jurassic to Cretaceous sediments. Widespread igneous activity around 139 to 132 million. Drill sample to east showed Jurassic to Eocene sediments overlying Precambrian, so they were able to find Precambrian crust overlaid by Jurassic to Eocene sediments. And then I guess this is their guess of what these layers are, is Cretaceous and then some other period. I'm not sure when that one is. Valanginian. It's a specific age. 139 to 132, which is the period I was just talking about, I guess. When the widespread igneous activity activity in that period is bounded there. So I guess this whole segment is considered that. And then the top of the Permian and Devonian. So something going on in Permian, Devonian, overlaying Precambrian based on a drill sample. This I found kind of interesting, this sill like this, kind of reminiscent of this undercurrent below the crust, just in a more detectable way, where undercurrent flowed in all directions throughout the earth, like a sill, but just continued to a point where it reshaped the whole earth. And this one more so met resistance, I guess. So they can kind of detect the sills down here. I think it's these features. And over here. I don't know if I wrote anything about that. Suggestion of folded lithologies in basement immediately. Something. Folds have a similar wavelength to the deformed Western Falkland something. Significant thickness of Jurassic to Cretaceous sediments. So that's just what I was just saying, pretty much. There's the drill sample DP 330, which I guess is over here, where they found Precambrian. Through Precambrian overlaid by Middle Jurassic, overlaid by these other periods. I don't know if you guys can see that because I might be atop it. Southern margin. So I wrote slopes down and abruptly abuts the Birdwood Bank, where the Scotia Arc contacts it. So it slopes downward and then abruptly abuts the Scotia Arc here, which is this region. Scotia Ridge. Birdwood Bank maybe is over here. Looks like it. The thicker segment of the Scotia Arc. So it slopes down and then runs into and there's folding here going on. Mind you, it's generally my interpretation that there was a current between these. Similar up here, a current went this way and pushed out an arc here as the continents segmented, particularly from over here that was flowing up this way and flowing over there as well to just fill this region as it pushed the continents apart, and then the connection between formed more coalesced out of what may also have been Precambrian crust, but very thinned piece that then got like deposited on during the extension of North America from South America, and then an arc formed from a current though flowing that way, forming an arc just like down here, current flow that way. Basically, the Atlantic was more peaceful than the Pacific, so currents generally escaped out of like vent points from the Pacific between the continents going eastward that then produced an arc there and there. And as it did that, it abutted the Falkland Plateau region, which then I presume contributed to this folding. Like this was probably sloped down more, but then a wave comes through. So imagine it's sloped down and a wave comes through that also is like spreading to a certain width. So it comes in and then also spreads and pushes it aside and leads to this kind of folding area here. That's kind of what I'm thinking. So there's with some colors. Not sure what they mean exactly, but still not sure what they mean exactly, but still. Next thing, northern Falkland Basin up here. I wrote samples of Devonian, so continental, but Devonian. It's unclear if there's Precambrian. There hasn't been like drill samples that were taken here to demonstrate Precambrian, but it really looks like the whole area is underlaid by Precambrian crust. It just hasn't been found in all the places. Here they found Devonian, at least the earliest, which is like 400 million, which is during the Earth's expansion process. So it could be that some portion of this kind of wedged in like the Spratly Islands as a Devonian continental crust, but ultimately isn't underlaid by Precambrian, but I suspect it's just all generally underlaid by Precambrian, but probably more complex than that, so it's possible some regions are not. Most of the rifting in this region happened in the Jurassic, and then people just go through North Falkland Basin. There's some grabins and some horse, I guess. So extension seemingly happened, which they're then filled with something, some kind of material that then overlays them and then gets flatter upward. Like the other places we've seen in that regard. So there, he pointed to some suggestion of tsunamis may have struck the Falkland Islands, but I feel like he didn't really find it persuasive. And then he definitely did not find this persuasive, a proposed impact crater here. And he's like, it's not that circular, just because by drawing a circle doesn't make it circular. There might be something of interest to it. Obviously it's not an impact crater, but it might be like the same general process. It reminds me of the Carolina Bays. Like there's a lot of Carolina Bays like this. These are all considered Carolina Bays because of their shape. But like, and they go down to Florida, down here. But like, if we look at Florida, like, is this a Carolina Bay? Is this a Carolina Bay? They're not called Carolina Bays. Are these Carolina Bays? They're kind of abnormal, is my point, and so they're not associated with Carolina Bays. So people researching the Carolina Bays don't really consider the additional nearby bays that are of similar nature, that likely are of the same process, is my point. Formed from the same process, just not in the same exact conditions. A little further from like the epicenter of where it's happening, so that they're more irregular. So it's possible that the process where like a current flow really focals into a focal point, produces a crater, like we talked about with Chicxulub, where it just boom, just the sheer pressure of compacting water leads to just forces downward that at some point just like literally probably are going up and down and vibrationally, but then just hit with enough force to create a crater at a 65 million, which also there's like 15 KT boundary impact craters. So it's possible something like pseudo of that nature happened here. It just didn't form such a distinct crater that it visibly looks like one, to a point where it's like a debate on if it is one. So people hypothesize maybe there was an impact there, but maybe there wasn't because it doesn't really look like one. There's not really any like impact lines in the seismic evidence as well. Like it's not visible. This is across this. This image is going across it, so we should see like a downward thing that then kind of goes across and goes back up. Probably with like a peak, like if we look at Nader Crater. If we look at this paper, they have such a cross-section of Nader Crater, which is another KT boundary impact structure. And if we go, so here's Nader Crater. We'll find a better image though, like this. It's got this uplift. It's got these faults surrounding like a more uniform area, so it looks like something impacted there. We don't see that here. To point against there being any such event here. So it's possible there was no such event. Then he pointed to this and was like, it doesn't fit very well. Falkland Islands is strongly evidenced to have been east of South America, Southern Africa. So like right here is strongly evidenced to have been over here. As long as you rotate the islands 180 degrees, which there's evidence for. So like this. These are possible locations, possible ancient positions of Falkland Islands that have been proposed. One kind of generally where they are with regard to South America, but not relating to Africa. Another more northern between Africa and South America. He seemed to think this one didn't really fit the data, I believe. And then this one is the one that really fits the data, but it doesn't really fit plate tectonics on. Honestly, if it just proves the Earth expanded. It's just another data point that demonstrates the Earth expanded because it fits the Earth expansion process way better than it fits plate tectonics. Because we like this image, this is on a plate tectonics model. This is not how the Earth was. Like this wrapped around here because the Earth was smaller radius. Where Falkland Islands were positioned where the data is showing they were It's just like hard to explain in modern interpretations because we use plate tectonics. Something to do with the deformation front. This is South America, or Southern Africa, sorry. This is Falkland Islands. So let me just read some stuff. Strongly evidenced to have been east of South Africa. Falkland Islands. As long as you rotate the island 180 degrees, offshore faults point to closer to 100 to 120 degrees, which is a better fit with the paleomagnetic data. The rotation is considered to have happened at 185 to 165 million radiometric dating. And he said it has to happen between two dike intrusions of 178 million and 135. So interestingly, there's a dike intrusion and then rotation of Falkland Islands and then another dike intrusion, which to me points to building up pressure. Islands rotate and then the pressure subsides because they're rotating with regard to the separation in part of the continents. Like they're not fully separated. The Earth is not fully expanded, but they're beginning to separate, so it relieves some pressure in the interim. But the dikes are like evidence of a high pressure buildup, and then it rotates and stabilizes a bit, but then later on the pressure returns enough where dike intrusion happens again at 135 million. Let's see when the Scotia arc formed. $120 to $83 million. So like a pressure buildup, which then led to dikes, which was relieved, I guess, by the acceleration in South America's westward propagation in the mid-Cretaceous and the formation of the Scotia arc. Which probably points to whatever undercurrents were interacting in Falkland Islands were able to vent more so over here at that time. Just a guess at a glance with that regard. Strong evidence for stratigraphic structural correlation with South Africa, Antarctica, or stronger evidence for stratigraphic structural correlation with South Africa and Antarctica lithologies than with South America. Which I believe maybe talks about in this slide, these slides. There's like this. It just needs rotated a little bit. Correlated the structures of the Utaniqua Basin to those in southern North Falkland Basin. Suggested that rotation occurred between rifting events that form the two sets of structures in the North Falkland Basin at 178. Reduced required rotation 120 has a better fit, so this is stuff I already read, but effectively reduces the rapid rotation rates required of the islands. One of the major weaknesses of the model is this rapid rotation rate. I don't find it that weak because it's kind of interpreted. It's one of the reasons is, well, how's that happening? It's plate tectonics, blah blah blah, plate tectonics, blah blah blah, plate tectonics. Like, if it rotated 180 degrees based on evidence, then maybe it did. But so the fact that sure 120 is a little easier to explain, but I wouldn't say it's a major weakness per se. It's more of a major weakness in the modern paradigm of plate tectonics. Okay, so that was those. Okay, that was all I had to say for now. I got some other notes on Bighorn Basin. And then I'm almost done catching up with my notes. I've been watching stuff and taking notes and watching stuff and taking notes and doing other stuff. I definitely got some more shallograms to go through. But I wanted to catch up with those things at least. And Bighorn Basin over here. I watched a video on this. I thought I'd kind of share what it was about in my perception and my interpretation. And alright, without further ado, I'll see you guys in the next one. Thanks for hanging out. Peace out.